introduced the concept of a two winding transformer through a inductive potential divider of this form. That is, if we give a input voltage of V1, then we will get a output voltage of V2, which is different from V1, and from here we arrived at the concept of two winding transformer, saying that these two parts can be separated out, unlike a resistive potential divider. The reason being, the power transfer from input to output in this case occurs not only by the conductive path like this, but also by magnetic induction. By that we mean, when we apply a voltage here, a flux is produced which links both part of the coil, and when a load is connected here, the current flowing through the load tries to change the flux. As a result, a reflection current is drawn from the primary side. A part of the power is transferred by the conductive path, but a part is transferred by the inductive part as well. While therefore, if we say this current is I1, this current is I2, then and this current is I3, then the phasor diagrams of I1, I2, I3 can be drawn as follows. Assuming negligible magnetization current, if we say this, the number of turns of this part is N2 and this part is N1 minus N2, then from balance of MMF we can say N1 I1 equal to N2 I2, so that the net magnetization current is 0 in an ideal transformer. Therefore, what is I3? I3 equal to I2 minus I1. In other words, I3 equal to I2 minus N2 by N1 into I2 equal to 1 minus N2 by N1 into I2 is same as, or I3 equal to N1 by N2 into 1 minus N2 by N1 I1 equal to N1 by N2 minus 1 into I1. From this expression we can see N2 by N1 is larger than 0. Therefore, we can see that the current I3 will be smaller than the current I2. That is because the I3 is the current due to induction, whereas the rest of the current flows by conduction. So, in a autotransformer, power transfer takes place both by electrical conduction and magnetic induction, and hence certain advantages result. For example, if the turns ratio N2 by N1 is close to 1, then I3 will be very small compared to I2, and therefore, the current carrying capacity of this part of the winding can be designed to be low, and hence there is a possibility of considerable saving in the copper, which is a disadvantage for this kind of arrangement. This is called a autotransformer. This advantage does not exist in a two winding transformer, where the entire power transfer is by inductive method. Let us look at a few examples of the advantages of this autotransformer. For example, let us compare the losses in both cases. For the two winding transformer, let us say this is the two winding transformer. A2, A1, A2, A1. Let this current be IA, this current be IB, number of turns here NA, number of turns here NB, resistance of this winding let us say is RA, resistance of this winding is RB. Therefore, the total copper loss in this two winding transformer will be IA square RA plus IB square RB equal to P copper loss in two winding. Now, if we join these windings to form a autotransformer, we can join this point to this and this point to this, that this tapping being the point where the voltage is same as the voltage between A2 and A1. Then the operation of the transformer does not change. At the same operating condition, this is now call it A3, A1 and A2. Say the current is again IB here, now there are NB number of turns and this number of turns is NA minus NB. Let this current be IA. In this case, the power loss is PCU autotransformer is equal to IA square into R1 plus IA, this current is IC, which is IA minus IB square R2, where R1 is the resistance of this part of the winding and R2 is the resistance of this part of the winding. Now, the current on the upper part of the autotransformer and that of the two winding transformer are same. Therefore, assuming same current density, the conductor cross section of the two winding transformer HV winding and upper part of the autotransformer are same. Hence, the resistances depend on the number of turns. Therefore, R1 can be written as NA minus NB divided by NA into R A, let us call it, that is 1 minus alpha R A, where alpha equal to N B by N A. To calculate the resistance R 2, we note that the number of turns of the LV winding of the 2 winding transformer and the number of turns of the lower part of the auto transformer are same. However, while the current in the LV winding is I B, the current in the lower part of the auto transformer is I C, where I C equal to I B minus I A. Now, again if we assume the current densities of this winding and in this part of the winding to be same, then the cross sectional area of the conductors of the LV winding of the auto transformer and the lower part LV winding of the 2 winding transformer and the HV winding lower part of the auto transformer should be inversely proportional to the current carrying capacity. Hence, if we say that the conductor cross section here is A B and the conductor cross section here is A 2, then A B by A 2 equal to A B by A 2 will be equal to the inversely proportional equal to I B divided by I B minus I A. That is A B divided by I B divided by A B, which is the current density of this winding, should be equal to I B minus I A divided by A 2, which is the current density in this part of the winding. Now, R 2 by R B resistance is inversely proportional to the cross sectional area. R 2 by R B equal to A B by A 2, that is equal to I B divided by I B minus I A. Hence, the total I square R loss in the auto transformer will be P C U auto equal to 1 minus alpha R A I A square plus R 2 is given by I B divided by I B minus I A into R B into I B minus I A square equal to 1 minus alpha R A I A square plus I B into I B minus I A R B. But if we neglect the magnetization current, then N A I A equal to N B I B. Hence, I A by I B equal to N B by N A equal to alpha. Therefore, I B minus I A by I B equal to 1 minus alpha, or I B minus I A equal to 1 minus alpha into I B. Hence, the copper loss in the autotransformer should be equal to 1 minus alpha into R A I A square plus 1 minus alpha R B I B square equal to 1 minus alpha into R A I A square plus R B I B square, which is the power loss in the two winding transformer, equal to 1 minus alpha into P C U two winding. So, we see for the same rating, if the two winding transformer and the autotransformer are supplying the same load, then the autotransformer will have lower loss. Not only that, we will find that the autotransformer will also use lower copper volume. For that, let us define A to be the cross section of the HV winding of the two winding transformer, and AB cross section of LV winding of the two winding transformer. Let LMA be the mean length of turn of HV winding, and LMB mean length of turn of LV winding. Then the total copper used in the two winding transformer VCU two winding equal to copper used in the LV winding, which is Na into LMA into AA, plus copper used in the LV winding, which is NB LMB AB. So, this is the volume of the copper used in the two winding transformer. Let us now compute the volume of copper used in the auto transformer having the same kVA rating. For that, this is the two winding transformer, number of turns Na, cross sectional area AA, mean length term LMA, number of turns Nb, cross sectional area AB, mean length of turn LMB. For the auto transformer having the same kVA rating and the voltage rating, number of turns here is Nb, number of turns here is Na minus Nb, mean length of turn here let us say still L M A, and here it is L M B. Now, let us consider the cross sectional area. This part of the autotransformer and the HV winding of the 2 winding transformer carries the same current if the 2 transformer have same kVA rating. Therefore, their cross sectional areas should also be same. So, this part has a cross sectional area of AA. However, the current carrying capacity of this part of the 2 winding of the autotransformer is IC, which is IB minus IA, whereas for this it is IB. Therefore, the current carrying capacity of the lower part of the autotransformer is IC equal to IB minus IA. So, if this part has a cross sectional area of AC, the current density is IB minus IA by AC. This should be same as the current density of the LV winding of the 2 winding transformer. So, this should be equal to IB minus IB by AB. Therefore, AC equal to IB minus IA by IB into AB, 1 minus IA by IB into AB. But we have seen for negligible magnetization current NA IA equal to NB IB, hence IA by IB equal to NB by NA equal to alpha. Therefore, the volume of the lower part of the autotransformer will the cross sectional area of the lower part of the autotransformer will be one minus alpha into AB. Hence, the volume of the copper in the autotransformer will be Na minus Nb into LMA AA plus Nb LMB to 1 minus alpha AB equal to 1 minus alpha into Na LMA AA plus Nb LMB AB into 1 minus alpha. Hence, this is also equal to 1 minus alpha volume of copper in a 2 winding transformer. Hence, we see that for the same kVA rating, the autotransformer will give lower losses as well as will use lower copper volume. However, as we have mentioned in the beginning, it will not provide electrical isolation between the two sides. Therefore, where the electrical isolation is necessary, we cannot use a autotransformer, but however, if the electrical isolation is not very important, it is advantageous to use a autotransformer, particularly when the quantity alpha, that is Nb by Na, which incidentally is also the voltage ratio. If this voltage is V1 and this voltage is V2, then we know V1 by V2 equal to Na by Nb. So, alpha equal to V2 by V1. So, if the quantity V2 by V1, that is the voltage conversion ratio is close to unity, then this quantity 1 minus alpha is almost 0. Hence, there will be a large saving in copper and also a large saving in losses. Hence, if the requirement of electrical isolation is not very important and the voltage conversion ratio is close to unity, then it is advantageous to use a auto transformer rather than a two winding transformer. Generally, auto transformers are suitable for a value of alpha between 1 to 0.5. Now that we know about the advantages of a auto transformer, let us pay our attention to analysis of an auto transformer. How do I analyze a auto transformer? For that, let us assume that this auto transformer is supplied with a voltage of V A on the HV side, draws a current of I A here, and the output is taken from here, supplies to a load Z L, passive load for the time being we will assume, with a current of I B. This point let us call it A, this B, this C. This current is I A, this current is I B, this current is I C, and the load voltage here is V L. The number of turns in this section is N B and in this section is N A minus N B. Therefore, we can write, it is to be noted that the coil of a auto transformer is wound on a magnetic core. Hence, both the parts of the winding links the same magnetization flux. Therefore, we can write that E B C, that is the voltage induced in the part with turns N B divided by E A B is equal to N B divided by N A minus N B, and they will also be in phase. From KVL we can write the induced voltage E B C equal to the leakage impedance of this part V B C, Z B C into the current I C plus load voltage V L, where V L equal to I B into Z L. Similarly, we can write the applied voltage V A to be equal to the drop across the leakage impedance of the section A B, that is I A into Z A B, plus the induced voltage in the section A B, that is E A B, plus the load voltage V L. Now, substituting from above equations, we can write V A equal to I A Z A B plus N A minus N B by N B into E B C, that is what E A B is, plus V L. On further substitution, we get equal to I A Z A B plus N A minus N B by N B into Z B C I C plus Z L I B plus Z L I B, or V A equal to I A Z A B plus N A minus by N B minus 1 into Z B C I C equal to I B minus I A to I B minus I A plus Z L I B into N A minus N B by N B plus 1. This can be written as I A into Z A B plus N A by N B minus 1 into I B by I A minus 1 into Z B C plus N A by N B into I B by I A Z L. Again, if we neglect the magnetization current of the autotransformer, we can write N A I A equal to N B I B, or I B by I A equal to N A by N B. Let us define this quantity to be A. This is also same as the open circuit voltage of the autotransformer. Hence, we can write V A to be equal to I A into Z A B plus A minus 1 into A minus 1, that is A minus 1 square Z B C plus A into A, that is S square Z L. Hence, the equivalent circuit of the autotransformer can be drawn as this is R A B, this is J X A B, where this quantity is Z A B, this is A minus 1 square R B C, this is A minus 1 square J A minus 1 square X B C, hence this part is A minus 1 square Z B C, this is A square R L, this is J A square X L, hence this quantity is A square Z L. This is the referred load voltage V L dash, and this is the referred load current I B dash. What is the relationship between V L dash and I B dash? V L equal to V L dash equal to it multiplies by the turns ratio, that is N A by N B into V L, and I B dash equal to N B by N A into I B, so that V L dash I B dash equal to V L I B. This is also same as I A, since we have neglected the magnetization current. So, this equivalent circuit is similar to that of a approximate equivalent circuit of a two winding transformer, except that for the lower part of the autotransformer we will have to use the turns ratio as A minus 1 rather than A. For a two winding transformer with the same number of turns, it would have been A square into the leakage impedance of this part. Now, that tells that not only a autotransformer will have lower loss and lower copper volume, it will also have much lower leakage inductance or leakage reactance. Hence, the voltage regulation of a autotransformer will also be better compared to a two winding transformer. How do we draw a phasor diagram for this autotransformer? For that, let us draw the autotransformer again. This is the voltage V A, the current I A, and let us say we are drawing a load current I B to a load impedance Z L, which we will assume to be inductive, and this is the voltage V L. So, let this be the phasor of the load voltage V L, and since this is a lagging impedance, this is the inductive load, the current I B will be lagging V L by the power factor angle. So, this is the current I 2 or I B. The current I A and I C are in phase with I B. However, so this is the current I B, the current I A is a fraction of I B, because for the current relations we have I B equal to I A plus I C, and also N A I A equal to N B I B if we neglect the magnetization current. So, this is the current I A and the rest is the current I C. Now, from the first equation, that is E B C equal to Z B C I C plus V L, we can get the phasor E B C, which will be this is the phasor E B C, but we know E A B equal to N A minus N B by N B into E B C equal to E minus 1 to E B C. Since autotransformers are normally used with A less than 2, E A B will be in phase with E B C, but of smaller magnitude. Now, let us use the other equation, that is V A equal to I A Z A B plus E A B plus V L. This is E B C. E A will be in phase with E B C, but of smaller magnitude. So, let us assume this is E A B, this is V L, this is V L plus E A B plus I A is in phase with I B, I A R A plus J I A X A. Hence, this will be the phasor V A, this is the phasor E B C, this is the phasor E A B, this is the phasor V L, this phasor is I C, Z B C, R B C, this phasor is J I C X B C. Similarly, this phasor is I A R A B and this phasor is J I A X A B. So, this will be the phasor diagram of the autotransformer. Now, let us solve a problem concerning the autotransformer to understand whatever has been taught so far. For that, let us take this example. You have a 10 kVA 1.1 kV by 440 volt single phase two winding transformer. So, this is the two winding transformer. this is A B, A2 A1, this is A2 A1. This rated voltage is 1.1 kV, 10 kVA. Rated voltage here is 440 volt. Again the kVA rating is 10 kVA. If we wish to connect it in terms of an autotransformer, what are the different possible connection? Obviously, there are two possibilities. One is this is the part A2 A1 connected in series with the smaller part A2 A1, and we take the output from here. So, what will be the voltage ratio here? The maximum voltage that can appear on this side is 440 volt. The maximum voltage that can appear here is 1.1 kV. Hence, the voltage ratio V1 by V2 or V2 by V1 here can be 440 divided by 1100 plus 440 equal to 440 divided by 1.1540. This is the voltage conversion ratio. What will be the current carrying capacity? The current carrying capacity of the section A2 A1 is I A2 A1 equal to 10 kVA, 10 into 10 to the power 3 divided by 1.1 kV. This comes to 9.091 amperes. The current carrying capacity of the section A2 A1 will be I A2 A1, that part it is again 10 kVA, because we have joined these two in series. So, their current carrying capacity do not change, divided by 440 volt. This comes to 22.73 amperes. Therefore, the maximum value of the current, output current I2 max will be the sum of these two. This should be equal to 31.82 amperes. Hence, the kVA rating will be V1 I2 A1 equal to V2 I2 max. This comes to about 14 kVA. Hence, when I connect a two winding transformer, the two windings in series, I get a autotransformer whose kVA rating increases to 14 kVA. There is another connection possible, where the section A2 A1 is connected on the top and the section capital A2 A1 is connected on the bottom. In this, that is here A2 A1 and here A2 A1. This part has a, and the output is taking across the high voltage winding. So, this part has a rated voltage of 1.1 kV and this part has a rated voltage of 440 volts. Hence, here the voltage conversion ratio will be V 2 by V 1 equal to 1100 divided by 1540, going by the same logic. Similarly, the current carrying capacity here I A2 A1 is equal to 22.73 amperes, whereas the current carrying capacity I A2 A1 is 9.091 amperes. Hence, I 2 max in this case also equal to 31.82 amperes. Now, the kVA maximum kVA, that is V 2 into I 2 max, comes to about 35 kVA. So, a 10 kVA 2 winding transformer can supply 35 kVA when connected as a auto transformer. It is easy to see here the value of alpha was much lower than 1, hence the increase in the kVA was not all that great. Here the value of alpha is close to 1, hence we get almost 3.5 times increase in the kVA rating of the auto transformer.